Okay. Consider this function t that maps m by n matrices to n by m matrices. So be careful. Your vector space V is different from vector space W. So here you have a function. This function takes matrices and gives you the transpose of those matrices. Show that T is a linear transformation. So to do that, we need to show that T preserve addition and also preserve scalar multiplication. Consider two matrices A and B from first vector space or the domain M of n and n. To show that it preserves addition, we need to just plug in A plus B into this function. This becomes A plus B transpose. But by the definition of the transpose of matrix, this is clearly the transpose of A plus transpose of B. But this is basically the definition of this function. The transpose of A is equal to T of A plus the transpose of B is T of B. So we just showed that this guy preserves addition. What about the scalar multiplication? We need to show that T of CA is equal to CTA. So again, guys, the vectors are not in the form of U and V. The vectors are in the vector space of matrices. So you need to use A. By definition, this is CA transpose. But again, going back to the transpose property, this can be written as C times the transpose of matrix A, which is nothing but CTA. So we just showed that it preserves scalar multiplication as well. So we're done. T is a linear transformation from the vector space of M by N matrices to the vector space of N by M matrices. Let's go back to calculus, everyone. Suppose C prime of A and B be the set of all functions whose first derivatives are continuous. Show that the differential operator, which we denote by dx, defines a linear transformation from the vector space of all continuous first derivative functions to the vector space of all continuous functions. So C prime says, hey, the first derivative are continuous. C itself says the function is continuous itself. So how do we show that this function, this operator, is a linear transformation? So it says, hey, d sub x of f is the differential of f with respect to x. We need to show that it is preserving addition and also it preserves the scalar multiplication. So what are we going to do? We're going to plug in the summation of two vectors from the domain. So f and g are two functions in C prime or C1 of A and B. Sometimes they use 1 here as well. So basically, this is saying that, hey, I have the summation of two functions. I'm going to take the differential. Of course, it is equal to the differential of the first function plus the differential of the second function. But by definition, this is dx of f plus dx of g. So we just showed that it is preserving the addition. Now for scalar multiplication, dx of CF is the differential of CF with respect to x. Going back to elementary calculus, you can write it as C times the differential of f. So this is nothing but C dx of f. What's the meaning of that? It means that the scalar multiplication is also preserved. So for sure, you can say that this is a linear transformation. So far we talked about linear transformation for matrices, the linear transformation that takes a matrix and give you a transpose. And now going back to calculus, we defined a linear transformation, which is basically taking the differential with respect to one variable x. Both of these are met. It preserves addition and also it preserves scalar multiplication. Now consider this operation. T maps P to R. What is P? P is the vector space of all polynomials. What is R? R is just a real line. What does this function do? It takes your polynomials and it calculates the definite integral, which definitely is a real value. So the definite integral is a real value. But is this a linear transformation? You need to check to see if it preserves summation and also it preserves scalar multiplication. Let's begin, everybody. Suppose P is basically a polynomial. You're going to take another polynomial as well. T of P plus Q is the definite integral of Px plus Qx, and the lower bound of the integral is A, the upper bound of the integral is B. But the summation of two polynomials and taking the integral can be written as the summation of the first definite integral plus the second definite integral. You're just basically calculating the first definite integral and the second definite integral, which is equal to, by definition, T of P plus T of Q. So the very first condition preserving the summation is met. Now scalar multiplication. T of Cp is equal to the definite integral of C times Px. But again, as you remember, C as a scalar, as a number, can be written in front of the definite integral, which is basically the definition of this function. This is C of Tp, so it preserves the scalar multiplication. It's indeed a linear transformation.